Welcome to the lecture series on bending stress in beams. This is a part of Strength of Material lecture series on bending stress in beams. Now, in the first class, we have learned the basic concept of what are stresses and how we are going to develop a simple equation. And I have already told you in previous class that we need some simplification to get an equation of bending stress in beams. And there is a theory which is known as theory of pure bending. This theory has already simplified, made some assumptions. Now let's learn about theory of pure bending. So the first question comes, what is pure bending? Now, part of the beam which is subjected to only bending moment is said to be in pure bending. We know when a beam is loaded, if we have a beam and it is loaded, right? Now this load induces two things in the beam. One is shear force and another is bending moments, right? Now these shear forces and bending moments, they both try to bend the beam, bend the beam, all right? But the beam does not want to bend, it resists, right? Resists. So this resistance against bending causes stresses, and these stresses are of two types. Okay, now if the stress is caused by shear force, due to shear force, right? Shear force, now this is known as shear stress. Now if the stress is caused due to bending moment only, bending moment, it's called bending stress, all right? And the combine these two stresses, if both shear stresses and bending stresses occur in a beam together, then they are called combined stresses, right? As you can see, this load causes shear force here, and it also causes bending moments, in fact at all the sections. Now these shear forces and bending moments, of course they will try to see if here is a shear stress like this, it will try to bend it like this. If this moment is like this, it will try to bend it like this. In a nutshell, both shear forces and bending moments, they try to bend it in a certain way. Now the bend, they try to bend the beam, and there is some strength in the beam which is responsible for resistance against bending, which does not let it to bend, all right, which leads to the stress. Okay, we have to find these stresses. Now stresses can be due to shear force, then it's called shear stress. Now the stresses can be only due to bending moment, then it's called bending stress, right? This is our motive. Our lecture series will be on bending stresses, okay? And in another lecture series we will talk about shear stresses, but right now we are talking about bending stress in the beams, all right? Now you can see bending stress is only due to bending moment, right? Here it is, only due to bending moment, right? It means if you want to find bending stress somewhere, that means there should be only bending moment, right? Or we can say the shear force must be zero. Okay, when there is only moment present and shear force is zero, then this condition is called as pure bending. This condition is called as pure bending, or in some books, some texts, they also say it's called as simple bending. Okay, now let me show you in the diagram how we can actually know which part of the beam is in pure bending and which part of the beam is not in the pure bending. So let me first erase all of this. Let us draw a simply supported beam with overhangs. Let's say this is a beam and these are the two supports. This one is a pin support and this is a roller support, right? Now let's assume loads are acting here. Let the load be W and here also the load is W. Okay, in this diagram I will tell you which part of this beam is actually in pure bending. Let this point be A, let this point be B, let this point be C, and let this point be D. Now let us draw the shear force diagram, SFD. Now if you don't know about how to draw the shear force diagram, please watch my video lecture on how to draw shear force diagrams. First of all, we will draw some lines here. Now let us draw a zero line, baseline of shear force diagram. On this line, the shear forces are zero. Now, when you see the C part, right? This point corresponds to the C part. This point corresponds to the A part because A is above it. This point is B and this point corresponds to part D. Now at C you can see there is a downward force load of W, right? So we will draw a line in the downward direction. This is W, right? Now first of all let's find the support reactions, because the first step in drawing shear force diagram is find the support reactions. This is also the first step in the bending moment diagrams. Okay, here is one reaction, here is another reaction. Now the total load is W plus W is 2W and they will be distributed half and half, right? 2W by 2 is W and here is W2. Again, if you don't know the shear force diagram, please watch my previous video lecture series on how to draw the shear force and bending moment diagrams. Anyways, here was a downward W, I draw a downward line, right? Now from C to A there is no load, so I will go parallel. Now at A there is upward W, so I will go up here. This is W again. Now A to B there is no shear force, so I will go flat here because on this line shear force is 0. From A to B there is no shear force or 0 shear force, so I draw a flat line here. Again there is an upward force of W at B, so I am going in the upward direction of magnitude W. Now from B to D there is no shear force, so I will go flat horizontal here, and at the D point of this beam there is a downward W force, so I'll go downwards, right? So this is the negative part of the shear force diagram and this is the positive shear force in this beam. Alright, we have drawn the shear force diagram. Now let us draw the bending moment diagrams. Let me extend these lines. And let me draw a baseline. This baseline is the base for the bending moment diagrams. this baseline have zero bending moment on it. Okay, now we are going to draw the bending moment diagram, BMD. Now you can see this is the free end C, so here is zero bending moment. So at C, because this corresponds to the point C, this corresponds to the point A, this corresponds to the point B, and this corresponds to the point D. Now at C there is zero bending moment because it's free end, so I draw a dot on the zero line. Now this W will induce an anti-clockwise movement at A like this, right, whose magnitude will be W multiplied by this length CA. Let this be L, let this be 4L, and let this be L. Now here will be at A there will be a moment is load multiplied by perpendicular distance, load is W, and the perpendicular distance between the load and the point is L, so W multiplied by L. Now again W is positive, L is positive, here will be some magnitude. Let's say W multiplied by L reaches up to here, right? Now because this is a point load, you should remember due to the point loads the bending moment is linear. Okay, I will draw a straight line. Now from A to B there are no moves, so I'm going to go flat here. Okay, now again the point D, it is free end, so it will be a zero bending moment. I will draw a point on the zero line, and at B how much is the moment? Here is a clockwise moment, right? What is the magnitude of this moment? W multiplied by L again, right? W is the load and the distance between the point and the point of moment is L, so W multiplied by L, right? So let's say the load here is up to W, because it's WL is here and WL is same, it means they will have the same height, so this height is WL. Because this is here is WL2, so this will be WL2. It means this line will be from A to B will be a horizontal line, and at D it is 0. When I connect, I will connect these 2 points with a straight line. Why? Because in the case of point loads the bending moment diagram is straight. Anyways, now look at the shear force diagram and bending moment diagram together. See, let's let's compare different parts of this beam, and we have to see in which section is pure bending. I mean to say which section have only moment and zero shear force, and which section have both. Now if you look at CA, there is shear force, right, and there is also bending moment. Is CA pure bending? Is it pure bending section? No. Why? Because pure bending means what? Pure bending or simple bending means what? Some magnitude of moment, all right, it is not zero, but shear force is zero. But in AC or CA there is some value of shear force. As you can see, the shear force is W here, right? From the shear force diagram from C to A there is some shear force, means it is not equal to 0, so CA is not pure bending. Now is BD pure bending? Now in the BD you can see some shear force, right? So this is not also pure bending. Now we have another section of this beam, AB. Now is AB in pure bending? Is AB a pure bending section? Now look at this. From A to B, the shear force diagram is flat, right? From A to B, there is, let V be the shear force, V is 0, right? From A to B. Okay, the first condition of pure bending is V equal to 0. This condition is possible for AB. Let's see, is movement 0 or not? Now, from A to B, movement is not 0, right? Movement is not 0. This condition is passed true. It means AB is in pure bending, right? So we can say in all of this beam only ABC bending, because here shear force is 0 and moment is not 0, right? This section is called pure bending section, and keep in mind you can apply the theory of pure bending in only the pure bending sections, right? So let me write here, you can apply this theory of pure bending, right? Theory of pure bending in pure bending sections only. Okay, only in pure bending sections. You cannot apply theory of pure bending or theory of simple bending in CA part, right? You can't apply here. Also, you cannot apply the theory on any of the sections between B and D, but you can apply the theory of pure bending at any section. Let the section be this, let the section be this or this or this, whatever. As long as it is between A to B, you can safely apply the theory of pure bending. So now you know what is a pure bending section, where moment is not 0 but shear force is 0, right? Shear force is 0. So let's move on. Okay, now there are some assumptions in theory of pure bending. Now, assumption A is this. What is the assumption A? Material is homogeneous and isotropic. Now we have two terms here. Homogeneous, right? And isotropic. Okay. Now look at this beam. If the material in this beam all over everywhere is same, right? Same material, then it is said to be homogeneous. Okay, and if the elastic properties are same in every direction, like if we consider this beam, okay, if elastic property at this point is same in this direction, also in this direction, also in this direction, and also in this direction, it means if the elastic properties are same in all the direction, then that material, that beam is called an isotropic beam. Okay, and in the theory of pure bending, you can apply theory of pure bending only when the body is homogeneous and it is isotropic, right? That is, it is made of the same material and the elastic properties are same in all the directions. Only then you can apply the theory of pure bending. Okay, now let's see B. The value of elasticity E is same in tension and in compression. What does that mean? Now let me consider a beam. This is a simply supported beam, for example, and you are applying a load here. Now this beam, what is going to happen to it? This will bend, right? It will bend something like this. Right? Now, due to this bending, due to this bending, the part, the above part will be in compression, right? This part will be in compression, and the bottom, it will be in tension, right? This will be in tension. Now we have Young's modulus of elasticity E. Okay, now if you want to find the Young's modulus of elasticity of this fiber, okay, this fiber, all of this, let me call this as a fiber, okay, or you can also call longitudinal section or axial section. Now this compressed fiber have some modulus of elasticity E because it's in compression, C, compression, I will denote it as EC. Now this part, the below this fiber, the bottom fiber is in tension, right? Tension, let me denote tension with T. So if you, this will have an elastic constant of Et. Now in order to the theory of pure bending to be valid, EC must be equal to Et, okay, and let us generally denote it with the general term E. If this condition satisfies, then only you can apply the theory of pure. Now let's read another assumption. The transverse sections are plane before bending and after bending. Okay, the transverse sections are plane both before bending and after bending. Okay, what does it mean? Now look at this beam. Uh, let me draw. Let me draw another beam. Basically, now when you bend, when you apply a load on this, now you can see this is plane, right? This is a plane section. This is a plane section, and in fact all the sections, if you see this section too, okay, this is also a plane, and if you draw another section here, for example, okay, and this section is plane also, and when you bend it, it will bend something like this, right? It will bend something like this due to load, right? Now again, this section, although it will bend, this shape will bend into this, but here this cross section is again plane, okay, this cross section is again plane, and in fact any plane, any cross sectional plane in any part of this beam, okay, it is assumed to stay planar, okay. This section is plane too, okay, and every cross section of this cross sections. What it means? So it is assumed when a when a beam is bended, the cross sections are plane before bending, like this is before, right? And this is after bending, right? So the cross sections of the beam remain plane before bending, and also after the bending they are also the plane. That's what's written here. The transverse sections, okay, the transverse section is this, or this is also called as cross section. The transverse sections are plane both before and after bending. Okay, hope this makes sense. So let me erase this so I can move to the okay. Another point is point D. The beam is initially straight and all axial sections bend into circular arcs with a common center of curvature. Let me read again. The beam is initially straight, okay, the beam is straight, and all the axial sections, right, the fibers, longitudinal axial sections are also called as the longitudinal fibers, they bend into circular arcs, okay, they bend into the circular arcs with a common center of curvature. So let me show you. Now look at this beam. Now you can see here I have just drawn these fibers, okay, this is a plane, right? All of this is a plane, it's like a slice, right? Longitudinal, like this, okay. So this is one axial section or the fiber, okay. We have another section here, another fiber like this, okay. The first thing is the beam is initially straight. Now this beam has not bended and you can this is a straight, okay, it is straight, there is no bend whatsoever. And another thing is, now this is a straight fiber, right? This fiber is also straight here because this is before the bending, right? Before the bending it is straight, but when it is bent, it bends into a circular arc, okay. When this load is applied here, when this load is applied all over, basically all over, what's going to happen, this they will bend, like this fiber, this will bend into something like this, right? It is going to, now this curve after the bending, it is assumed to be shape of a circular arc, okay. If you complete this circle, right now it is only the let us say this is a circle, okay, and I am considering only this part of the circle because it is the part of the circle, this is called as arc, right? Circular arc, circular arc, okay. Now this is the part of the circle, that's what's assumed in the theory of pure bending. I mean to say, if you are going to, you know, interpolate here, this is going to be the part of some big circle, okay. So this is point one was it is straight, this was point one straight, right? Point two is when they bend, they bend into circular arcs, right? And point three here is they bend, now this is the fiber, it will bend into a circular arc, right? This will also bend into, this fiber will also bend into a circular arc. When I interpolated this to make a big circle, here will be let me show it here. Now this is a circle, right? Here will be some center. Similarly, when you interpolate this like this, okay, it will have a center anywhere, let the center be here. And when you interpolate this circle, now the big circle, this will also have center this, and this fiber, okay, when you interpolate this will have the center at this point, means they will all form a concentric circle with a common center. Okay, it means they are concentric circles. Okay, now I can also make you understand by making, some clean circles. Let me draw a circle here. Okay, let's assume this one, the first fiber, has bent into the circular arc. Okay, and when you interpolate it, it is going to be a big circle. Okay, basically it is just this much is not the bending, because how it is going to bend there. This is the fiber and it will bend, of course, like this. And now all of the above is just an interpolation to complete the circle, right? Anyways, if I draw another circle, okay, now this part, the second fiber, right? Let me denote, this was first fiber, this one. Let this be second fiber, let this be, this arc is for the second, right? This is second. All of this, it bent and it made another circle. Similarly, the third one, it will also bend and it will make another circle around this, right? It will also make a circle around this. Now let us say the green, this one have a center like here, right? Let me show you here. Look at these circles. You can see all of these are concentric circles with a common center. What is the center of this smaller circle? This. What is the center of this circle? This. What is the center of this one? Same. All of these circles, they are concentric. Okay, that's what is told in this. Section is bent into circular arcs. That was the second point, with a common center of curvature. Okay, now this is the center of the circle and it's also called as center of curvature. Okay, center of curvature, not a big deal, just center of the circle, that is all. Okay, all of they have a common, so it is, the third point is common center of curvature. Is large as compared to the dimensions of cross sections. Okay, now if you want to know the radius of this, it is from here to here, right? And the radius of this green one is from here to here, whatever it is. But if you see, let the radius, this one be r, or this is r2, all this r, r1, r2, r3, this is so much large. Let the dimension of this cross section, okay, whatever you see here, let me show you. This is the cross section, right? This is the cross section. It will have a depth, suppose the depth is d. Now this r will be so much greater than d. Okay, the dimension, this radius is more than the dimension of the cross section or transverse section. That's what the point is. And the point f is, each axial section is free to expand or contract without any influence by other section below it. What it is saying, what I'm saying now, as you can see here, now this is section 1, right? This section 1 is bent with this green line like this, right? Now this section, this is section 2, is bent with the help of, it is shown with the help of this red color, right? With the help of this red color. Now this green is independent of red and this red is independent of what is this color, blue, and this blue is independent of green. In short, they are independent of each other. Section 1 will bend like there is no red. section. Okay, it does not care. Okay, the one will bend in such a way like 2 and 3 does not exist. Okay, 2 will bend in such a way like 1 and 3 does not exist. 3 will bend, it will also bend independently like 2 and 1 does not exist. It means they will not interfere in bending of each other. That's all. It was part F. Okay, now we have covered everything. If you want PDF of this, it is in the comments, and the next class will be on, we will find the equation. Okay, equation of theory of simple bending. Okay, theory of simple bending, that will be the next class. That's it. If you have any problems, please contact me. If you have any doubt, please comment. And also, if you need tutoring from me, I also offer tutoring in strength of materials. Also contact me for that.